All right, this is Mr. Crozier. I'm going to give you help on problems 1 through 20 of our review packet. First problem, trying to solve for x here. Well, I know that if it's 1, it's equal to 0. So I don't want it to be 1. I want it to be greater than or equal to 1, so I go above 0. Solve this inequality. You get this one here. On this one, symmetric to the y-axis means same on left and right, and cosine is definitely same on left and right. This is a parabola that's been shifted over. It's not symmetric. And this last one here, the graph's difficult to come up with, but if you know that symmetric means if I put in x, I get an output, and if I put in negative x, I get the same output at the same height right here. That would be this right here, because if you take the absolute value of x, you could just get x, and if you take the absolute value here, it turns into another x. So these are the same on the left and right. And this is the rule that you need to know to find stuff that's symmetric to the y-axis. If it's input and output, if you input x and negative x, and you get the same thing, it's symmetric. Some trig identities. Hopefully you know some of these, but if this is our double angle formula, it works out this way. All right, now we get to the calculus part here. Number 4. The best way I did this problem, I mean, if you had a calculator, you could graph it real easy and see where it goes. But if you didn't have a calculator, since we're going to infinity, nothing matters except the variables. I mean, if you have infinity plus 5, that's not significant. If you have 4 and you're taking away infinity, it doesn't really matter where you started. So at the top, all I have is the square root of b squared. At the bottom, I have a negative 3 and a negative b. And I could change this negative b into negative 1 times b, and then my b's would divide out. So all I'm left with is 1, negative 3 times negative 1 is 3. Graph it and you'll see. On this one, going to just a tiny bit bigger than 2, right? We're going to 2 from this side, so it might be 2.00000001. And if you put that right here, if you put this right here, that's just 2. But if you put that right there, that's 3 divided by a very, very, very little number. And it keeps getting smaller, so this keeps getting larger and larger and larger and larger. This keeps going closer to 2, this keeps getting larger, and we say it's going to infinity. So the limit here is that it's going to infinity. And actually, a lot of times they say if it's going to infinity, there is no limit here. There is no limit to this. It doesn't have a limit, but this paper says it's going to infinity. So you have to be careful. Sometimes they'll say the limit's infinity. Sometimes they'll say there is no limit because infinity is not a number. So either one, in this case, it goes like that. Down here, plug in 1. Well, if you plug in 1 there, you get 0. And if you plug in 1 there, that would be a cosine of negative 1, that would be 1, and you'd get something divided by 0 here. Or you get 1 cosine of 0 is 1 minus 1 is 0. So when you have this, you can use L'Hopital's rule, which says you take the derivative of the top and bottom. And the derivative of the bottom is 1, the derivative of the top is negative sine t minus 1. Now you can plug in 1, and when you do plug in 1, you get 1 over 0, so the answer is 0. So if you get this form of 0 over 0, or infinity over infinity, take the derivative of the top and bottom. Number 7 says, what's the limit as you get very close to 3? Well, what if we just plug in 3? If we just plug in 3, we have this. So if you can plug in the number, plug it in. Down here, we try to plug it in. Gave us 0, didn't work. Up here, we can plug in 3. All right, on this one again here, plug in 0, you get 0 over 0. Take the derivative, d dx both sides, and you have this. Now you can plug it in. All right, number 9, finding the value where it's continuous. Well, let's simplify this down, and we have factor out here, gone, gone. We're left with x. So this equation is really just x. And the graph of x looks like that. However, there's a hole right here at 1, 1 because it can't be 1. So at 1, 1, there's a hole. So what number do I need to fill that hole? Well, the number I need to fill that hole is a 1. So I need this to say 1. So this is the function, but if you plug in a 1, it can't be 1. But if you plug in a 1, it is continuous. Now if you would have plugged in a 2, the point would have been up here. Then your graph looks like this, and it's not good. So you have to plug in a 1, so it's continuous. Number 10, discontinuities. 1, 2, 3, 4. There's a jump here, there's a hole, there's an asymptote, there's a hole. Those are discontinuous. Where is there no limit? Is there a limit at 1? No. Is there a limit at 2? Yes, there is a limit at 2 because they're both going to the same thing. Is there a limit at 3? No, and again, this is where it's going to infinity. So it's going to infinity, so there's no limit there. Is there a limit at 4? Well, yeah, they're both going to that value right there. So these don't have limits. Where is it not differentiable? Well, we're going to start with these points right here, because if it's not continuous, we don't have a derivative there. So those don't have derivatives. And then this point right here is a cusp, meaning it's a point, meaning we don't know what the tangent line is here. Maybe it's there, maybe it's there, maybe it's there, maybe it's there. There's a bunch of tangents there. All right, number 13, simple quotient rule. Low d high minus high d low. Number 14, the only way to get this exponent down to the main level is to take the natural log. So when you do the natural log, it allows you to pull that down. Then you can take the derivative of both sides, and you have the chain rule here. Multiply this y over there. And now what we do is we take this y out and we substitute back in here, so it makes it look like this. It gives us a derivative. Instead of, this is a nice derivative here, but it has a y. If I know what y is, I can put that in there. Kind of a trick problem here. They're starting you with velocity. So if you want acceleration, all you have to do is take one derivative. Usually acceleration is usually the second derivative. However, we're starting with velocity, so we only have to go down one derivative to find the acceleration. Number 16, take the derivative, plug in 3. Number 17, relative extrema are the maxes and the mins here. Those are the relative extrema. Number 18, and what you do here is after you take the derivative here, you have this chain rule, or a product rule, sorry, lefty right, righty left. And then you can factor out this term here, which is a 3x squared, which is that. And now you have this times this. This is going to lead you to negative 1/2 for 0. There's nowhere here that you're going to get 0, right? Because you can't have an e as an exponent and get down to 0. You can't get down to 0 here. So this is never going to lead to a solution. This will lead to a negative 1/2 being 0. Problem 18 takes a lot more work here. Number 18, we're starting with this equation, and we're trying to find the normal line, which means here's my graph. Tangent is tangent. Normal is the opposite reciprocal. So the tangent slope you're going to find through this work is 3, but the normal slope you're going to find is negative 1/3. This one is 3. This one is negative 1/3. And I showed some work here how you go from the derivative, plug in pi over 2. Secant is 1 over cosine, so it comes out this way. Plug it in, the derivative is 3. And then once you have this, the slope equation is here, because we put in the normal one. And then now all we have to do is an equation and a point. And I went ahead and did a point slope way. Multiplied by 3 to eliminate this fraction, multiplied by 2 to eliminate that fraction. Put it in the standard form that they wanted. They wanted it in standard form, which is ax plus by equals c. You can put it in, we have all different kinds of equations for lines. Y equals mx plus b is probably the basic. We have y minus y1, mx minus x1. here, point slope, slope-intercept, standard, that's what they want, and it's there. Number 19, you have find the area of the largest possible rectangle that has two vertices on the x-axis. Well, here's the x-axis, and there's the curve. So here's my curve right here. It goes up and down, and I'm going to build a rectangle in here. And the width of my rectangle is going to be this distance here. It's going to go from x to negative x. So that's 2x's. That's the length. And the height of my rectangle is the output of the function. So it's this function. So this is really length times width, or base times height, whatever you want to call it. So we have this function. Well, how do I find here's a function. How do I find the maximum value of the function? Well, I just take its derivative, set the derivative to equal to 0, find out at this point it has a relative extrema right at this point. At the point root 3, I have a maximum. So this is a maximum value. So I take this root 3, plug it back into this equation, do the computation, and there's my output. All right, problem 20. Very complicated when you first start it, but it's actually not that bad. You're given, it's a related rates problem. And what you're told is that you have a cone. They give you the formula for the volume of the cone, and they ask you to find dH dt. So I'm going to take the derivative of all of it with respect to t at some point. And the pieces of information they give you are that dV dt is 10. They tell you that the height is always half the diameter, and they tell you that the height is 5 in this problem. So these are the pieces of information that are completely given to you. Given, 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 given. Now what I did with this was I said, look, if I have the height is equal to half the diameter, well, the height is equal to 1/2 2 radius, because 2 radius make a diameter. And then I said, look, well, if I simplify this, that h and the r are the same. So h is 5 and r is 5 in my equation. All right, so, and watch this transformation, then I think we're ready to start. If the volume is 1/3 pi r squared times h, I already said that h and r are the same in this particular problem. So this right here is really h cubed, because I have 2 h's and another h cubed. Now I think I'm ready. Now I take the derivative with respect to time. dV dt is equal to pi h squared dh. Plug in a 5 here, divide that over. There's dH dt, 10 over 25 pi, 2 pi over 5. These problems, the key is this. Write down everything you know. You're given 1, 2, 3, 4 things. You're usually taking the derivative with time because they are related rates problems. And think about what you have here. And think about what substitutions. I wanted to get rid of this r because I really don't know much about r except that it's the same as h. So I got rid of it, take the derivative, some simple algebra, and you will be there. All right, hope this helps with 1 through 20. We'll continue with the next ones tomorrow.